A Gaussian surface is an imaginary surface created solely to facilitate a mathematical calculation, and we are going to know more about a Gaussian surface in this episode of Physics is Easy with Mr. Jesse. In this lesson, we are going to state Gauss's law and apply Gauss's law to determine the electric field. Gauss's law states that the electric flux through any closed surface is equal to the net charge inside the surface divided by electrical permittivity, or in equation form, we have this. This is Gauss's law, where permittivity is just equal to 8.85 times 10 to the power of negative 12 coulomb square per Newton meter square. So this is electrical permittivity.
Now consider this point charge. So with this positive point charge, if we are to draw its electric field, the electric field lines would all be pointing radially outward in all directions. And if we are going to describe the electric field or solve for the electric field of this point charge, it is necessary for us to draw a Gaussian surface. Now, a Gaussian surface is just an imaginary surface that would allow us to mathematically obtain the electric field of this point charge here. So let's draw that Gaussian surface. It's going to look like this. So it basically is a sphere. So imagine a ball with this positive charge on its center. So the electric field would be going out in all directions. Now, so for that means that if I'm going to look at this small area here at this point of the Gaussian surface, I could see that the electric field would be pointing perpendicular to it. So if I am going to enlarge this part here, it is going to look like this. This is the surface of the sphere, and this is the electric field. So therefore, the area vector at that particular surface is also directed that way, so the angle between them is equal to 0 or 0 degrees. Also, if I'm going to look at this part of the Gaussian surface, so again, electric field would be pointing towards that direction. So if I am going to enlarge this part, it would look like this. It's going to look like this. This is that surface, and this is my electric field. And also at that particular point, the vector or area vector is also pointing towards the same direction as that of the electric field. So again, at this point, angle is also equal to 0. And hence, we could say that in every part of the Gaussian surface, right, in every part of the Gaussian surface, the electric field is always parallel to that of the area vector, which means that the angle is always equal to 0. And we have learned that electric flux is equal to EA cosine theta. And when theta is equal to 0, this means this entire quantity is just equal to 1. So therefore, our electric flux is just equal to the magnitude of the electric field multiplied by the area. And since our Gaussian surface is a sphere, therefore this area here is the area of the Gaussian surface. Gaussian surface. And in geometry, we have learned that the surface area of a sphere is just equal to 4 pi r squared. Therefore, we could say that the electric flux in this particular example where the Gaussian surface is a sphere is just equal to the electric field multiplied by area, and that's going to be electric field multiplied by 4 pi r squared. So we have the electric flux given that the Gaussian surface is a sphere. So earlier we have learned that according to Gauss's law, the electric flux is just equal to the charge enclosed divided by permittivity. And we have learned as well that if we have a Gaussian surface, the electric flux through the Gaussian surface in this particular example is just equal to the electric field due to the charge Q multiplied by the surface area of the Gaussian surface. Now, this is electric flux, that's also electric flux, therefore we could equate these two equations, or we could combine these two equations. So we will have Q enclosed over permittivity, and that's equal to electric flux, is just equal to the electric field multiplied by the surface area of the Gaussian surface. So again, the reason why we would utilize Gaussian surface is for us to be able to determine the electric field due to a charge. Now let's manipulate this equation. So we will have electric field is equal to Q enclosed divided by permittivity times the surface area. And we could expand this further. We have Q enclosed is divided by permittivity, and our area is 4 pi r squared. Again, this is the surface area of our sphere. We can rewrite this further as E is equal to, we will rewrite this part of the equation. So I will have 1 over permittivity 4 pi multiplied by Q over r squared. So this expression actually is the same with that expression. And now this part here is actually a constant because permittivity is a constant. Permittivity is constant, 4 is constant, and pi is constant. And this constant is denoted by Ke, which is something that you already have encountered in the previous year or previous term. And therefore, we could rewrite this entire equation so that we will have the electric field is equal to Ke Q over R squared. And this, in fact, is the formula for the electric field of a point charge, just like this Q over here. So we have learned that if we have a point charge and we are asked to solve for the electric field of that point charge, we have the equation E is equal to Ke Q over R squared, where Ke is just equal to a constant, which is 9 times 10 to the power of 9, and the unit is Newton meter square per coulomb square. So that is the electric field due to a point charge. Now let us derive the expression for the electric field due to a hoop. So we have our hoop here. So imagine or consider this hoop to be charged with Q. Now again, in order for us to get the electric field, we have to identify our Gaussian surface. Now a Gaussian surface is something that has symmetry. And when we say symmetry, that means that when we say symmetry again, that means that in that Gaussian surface, electric field is perpendicular to all points in the Gaussian surface. Okay, so here, if we have a hoop, then we could actually draw a Gaussian surface that would look like a sphere inside. So I could draw this Just imagine this to be a perfect sphere inside the hoop, and also another Gaussian surface outside the hoop. So just pardon me for this very imperfect sphere, but just use your imagination to consider that this, I would call this outer sphere or outer Gaussian surface, and this is my inner Gaussian surface, and they are all spheres. Okay, so if the radius of the inner Gaussian surface, I could call that Ri. Now the radius for the outer Gaussian surface, I could call this R sub O. Now according to Gauss's law, electric flux is just equal to Q enclosed, or Q enclosed, yes, divided by permittivity. And we were able to derive that the electric field through a spherical Gaussian surface is just equal to Ke, Q enclosed, divided by R squared. Again, this is the expression for the electric field through a spherical Gaussian surface. And since our Gaussian surfaces here, both the inner Gaussian surface and the outer Gaussian surface are spherical, then we could use this equation. Again, take note that this Q here is Q enclosed, meaning the Q that is inside the Gaussian surface, and this R here is the radius of the Gaussian surface. So if we are going to look at the inside part of the hoop, so we have E inside, electric field inside, is equal to Ke, and Q enclosed divided by R, the radius of the inner Gaussian surface, so I call that Ri. Now take note, if we look at this Gaussian surface here, is there a charge that is inside that Gaussian surface? So the answer is no. In fact, we don't see any charges inside. There's no Q enclosed, therefore this Q enclosed here is actually equal to 0. So therefore we could say that the electric field inside the hoop is equal to 0. However, if we are going to look at the electric field outside, or we call that EO, meaning electric field outside the hoop, that is equal to Ke, Q enclosed over RO. And in fact, our Q enclosed is just equal to Q, so we could say that the electric field outside is just equal to Ke, Q, which is the charge that is enclosed by the outer Gaussian surface, divided by RO. So in fact, the electric field due to a hoop is just equal to E K E Q over R sub 0, or R sub O rather, or simply K E Q over R, which is similar to that, or rather R squared, I forgot the squared here, square, square, square. So again, this expression is just very similar to the electric field, similar to the electric field due to a point charge. And this is due to the fact that the Gaussian surface that we have utilized is spherical. And there is no other Gaussian surface that we could use to solve for this one. It's just a spherical Gaussian surface. So there are other Gaussian surfaces, but this particular example, a Gaussian surface that provides us with symmetry, is a spherical Gaussian surface. Now let's look into the electric field outside a uniformly charged sphere. So if this is our charged sphere with radius a and the charge of that sphere is q, so our Gaussian surface would actually be a sphere as well. So again, a Gaussian surface is a surface that provides us with symmetry, meaning all of the electric field lines would point out radially outward and will therefore always make an angle of 90 degrees with respect to the surface area, or an angle of 0 with respect to the area vector. And again, since our Gaussian surface is actually a sphere, then we could just use the same equation as that of a point charge or a halo or a hoop, wherein the electric field is equal to Ke, Q enclosed in the Gaussian surface, divided by r squared, or the radius of the Gaussian surface. So our electric field in this case is equal to Ke, our Q enclosed, or meaning the charge that is inside our Gaussian surface, so that is actually Q, that is the charge inside the Gaussian surface, divided by the radius of our Gaussian surface, which is r squared. So as a matter of fact, this is the formula for the electric field outside a uniformly charged sphere. So if you notice, the electric field of a uniformly charged sphere outside, rather, the electric field outside a uniformly charged sphere is the same as the electric field of the point charge, and it's also the same as the electric field of the hoop. In summary, the electric field due to a point charge, the hoop, and outside a uniformly charged sphere is actually this equation. In a separate video, I'm going to discuss the electric field inside a uniformly charged sphere. But for now, that concludes this tutorial. Once again, always remember, physics is easy with Mr. Jesse.